Finish chapter 2 and start with time-dependent situations. So let me see, where did we start last day? I think we end up here. So last section we were discussing is correlation functions. I was discussing, just summarizing them quickly for you, that they are important objects in the theory. Maybe the most relevant one is the two-point function, because higher order correlation functions can be obtained from it in a free theory, and the two-point function involving momenta can be obtained from it using time derivatives, etc. And I was calling it G+, and the most important one of the important properties of this guy is that there are non-zero correlations for points separated spatially. So spatially separated, so it seems that our theory is violating causality, or have the possibility of violating causality. But we were arguing that causality has to do with observables, so to see if our theory really violates causality or not, we have to ask if any arbitrary couple of operators, of observables, evaluated at spatially separated points commute or not. And this is what I told you that I was going to give you the result today. Let me do it quickly, and then talk a little bit about green functions in the quantum theory, make a few comments, and finish the chapter.
Ivan.
Go ahead, please.
Yeah, today could you please try to write a little bit bigger than last time?
Okay, please let me know if I don't do it, because I will forget.
Okay, good. Thanks.
So bigger than this?
Bigger than...
He's not... Can you go to the right? In the camera? More? Okay.
Yeah.
Bigger than this?
Yes, that is particularly small.
Yeah. Please don't hesitate to let me know if I write smaller, because... So, first of all, I was emphasizing that this, commutator of two observables at different points equal to 0, spatially separated, is a state-independent statement. There is no state here. This has to be true for any state. I want to see if this is true or not. So, first of all, it is easy to realize that any physical observable is going to be written as powers of phi and pi, of the field operator and the conjugate momenta. And one can always, if you have a product of a linear combination of products of phi and pi's here and here, you can always use the properties of the commutator to reduce it to commutators of phi's between phi's between phi's, or between pi's and phi's and pi's. The commutator between pi's, anything involving pi's, can be obtained from anything from the commutator of two phi's by taking time derivative. So this is true. So I don't know if I was giving an equation. So a number. Equation 7. What I am just arguing quickly is that equation 7 will be satisfied if and only if the commutator of just two field operators are 0 for space-like separations. So this is what we have to check, if this is 0 or not for a space-like separation. This is enough to guarantee equation 7. So, now, since this commutator is a C number means it's proportional to the identity. It's just a classical number times identity. You can check that this is a C number just using the expansion, increation, and annihilation operators, and using the commutation relations. This is going to give you a C number because the commutator of annihilation and creation operators is a C number. So you are always going to get a C number. Then it is true that this commutator is equal to its expectation value in any state, in particular to its vacuum expectation value. Because this is a C number, so vacuum and vacuum give you 1, normalization 1, and you get exactly the same. Now, you know, the commutator by definition is just phi of x prime minus phi of x prime phi of x. So this is just the 2-point function between x and x prime minus the 2-point function between x prime and x. And by definition, we define this, so the commutator, we define it as G. So it's another 2-point function. It's really the difference between 2-point function, and this is called the commutator, G. And so the question is if this G is 0 for spatially separated points or not. And you know, it is simple to realize that G plus, so the 2-point function that we worked out the other day, is invariant under the change x by x prime for a space-like separated points. You can check that from the explicit expression that I wrote the other day. This expression, for instance, that you have a square there, so it doesn't matter if you change the order for spatially separated points, for which that is positive. So it doesn't matter. So you can see from here that you have j plus x prime minus j plus x prime x. They are invariant. Therefore, we obtain that the commutator is equal to 0 for spatial separations, space-like separations. And this proves that our theory respects causality.
Can you please again give a reason for that first line?
The first line is that this is a C number. So this is a number, a function, times the identity operator. So this is always equal to its expression value. Because imagine that this is, I don't know, is some function that I am calling G times the identity operator. You know, this is going to give you 1 because this vacuum is normalized, and it's going to give you the same as this guy.
Why is it a C number?
Because you know you can write phi as a combination of A and a dagger.
It's a number operator times.
No, sorry. Phi is integral of mode A of k plus mode A dagger of k, and so this is going to end up in commutators of A and a dagger, and they are C numbers. You know, they are 0 or the delta function. So you can check easily that these are a C number. I didn't do it. I just said that you can easily check that this is a C number. And then what you get is the difference of 2-point function, and as I said, the 2-point function is symmetric under change of points if they are spatially separated. Therefore, our theory preserves causality. So the fact that the vacuum has correlations at the space-like separations doesn't imply that our theory violates causality, and that is an important point. In this axiomatic formulation of quantum field theory by Wigman, one of the axioms is this condition, and it's normally called micro-causality. So you impose as your principle that this is true. We didn't impose it, we just started from the formulation and we got it as a result. That is completely equivalent. So this is what I wanted to say about correlation functions. Now I want to mention, to summarize quite fast about green functions. So imagine that all of you knows what a green function is. A green function of a differential equation is a function who satisfies the wave equation. We call it f. They are not really functions, they are distributions, and they satisfy the wave equation with a delta function as the source. So they satisfy the inhomogeneous wave equation with a delta function as source. And they are always distributions, not functions. And normally there are many green functions. They are obtained just from the wave equation and boundary conditions. And depending on the boundary conditions that you use, you get different green functions. So there are a few of them which are typically used in physics. Is what we call the retarded green function. We are going to call it G R x prime. Normally, when for the retarded green function, one uses boundary conditions of free fields in the past. This is what produces the retarded green function. Boundary conditions of free fields in the past. And just that you know that is a real function, is real, and as a function of x, it has support in the past light cone of x prime. This is why it's called retarded green function. It only has support on the past light cone of x prime. If you evaluate x outside the past light cone of x prime, that gives you 0. Another important one is the advanced green function. We call it G of A. It arises from the wave equation and boundary conditions of free fields in the future. It is real also. And as you can imagine, as a function of x, it has support only in the future light cone of x prime. Out of that is identically 0. And it happens that you can check yourself that the commutator can be written just as the difference of the advanced minus retarded green functions. And this is we use it quite a lot in quantum field theory. This relation that the commutator can be written as the difference between the advanced and retarded green function. As you know, probably another very useful green function in quantum field theory, in particular in Minkowski spacetime, where we are computing perturbatively some scattering amplitude, is the Feynman propagator. I'm going to call it GF x prime. And the Feynman propagator, by definition, so it's a green function also, and by definition is the expectation value, the vacuum expectation value of the T-order product of two fields. This is the T-order time order product, and probably, as you know, the time order, what it does is gives you I am writing bigger today, so I need more space. This is the step function. So it's a step function of phi x prime. Of course, there are operators all the way around that I keep forgetting. X prime minus the step function t prime minus t x prime minus x. So it selects this couple if t is larger than t prime, or this couple the other way around. So just put them in a time order way.
Should be plus these two terms.
Plus. Thank you. And it seems that it's not Lorentz invariant, but this quantity is Lorentz invariant because it's spacetime. It is well, it's not difficult to show. So just Feynman propagator is complex, is Lorentz invariant, and has support. It's a Lorentz invariant distribution and has support everywhere in Minkowski spacetime. In reality, there is what people call a zoo of green functions and propagators in Minkowski spacetime. There are many you can define. I'm not going to write it explicitly, but there is a very nice way of writing all of them in a really compact way. So it's just an integral in the complex plane, and depending how you avoid the poles, you get the advanced, the retarded, the Feynman propagator, or the 2-point function. So there is a really compact way of doing it. But because I am going to abandon Minkowski spacetime in 10 minutes, I'm not going to spend half an hour just doing it. But if you are curious, go to any book of quantum field theory, and you will find a really compact, complex integral where all these different functions appear depending how you avoid the poles in the complex plane.
I'm sorry, what was that for?
Minkowski spacetime
Oh.
in 4 dimensions. In general, you can define it for any spacetime dimension.
I can't remember, but when you wrote that minus sign, did you think, is it minus for fermions?
No, the time order product is always in that way.
Okay.
It's just time order product is just you just choose the order, this or this, depending which point is to the future of which one.
Is the time order of the product of the fields itself Lorentz invariant?
Yes.
Okay.
And it's not difficult to do. This guy is not Lorentz invariant, but the combination is Lorentz invariant.
Okay.
We can spend 5 minutes showing it later on if you want. So this is why I mention it explicitly, because it seems that it is clearly not Lorentz invariant, but it is. Comments, and I finish with a few comments which are kind of important. So the first one is just to tell you that in addition, so I introduced you 2 propagators, the standard, sorry, 2 correlation functions, G plus and the commutator, and just tell you that there is another useful correlation function. It's normally called G with a 1 on the top, although you may find different notations. And its definition is the following. Remember that the correlator, the G, is just the expectation value of the commutator. So you can also define the expectation value of the anti-commutator. where anti-commutator is phi of x, phi x prime plus phi x prime, phi x. This is normally called the Hadamard two-point function. It has information similar to J plus. The only thing is that you have is symmetric under x and x prime, so it's just mathematically more convenient. And you can see yourself that it is just J plus J plus of x prime x, and will be useful in core spacetimes. So if you want this, the symmetrized two-point function, that's all. So I can give you, just for completeness, expression of it in Minkowski spacetime at the risk of having some factors wrong, but I think I did right. So just for completeness, root square of delta x squared. This is the step function again. Delta x y1 m root square of delta x squared. And this expression is not that important. What is going to be more relevant is the next line. We have a minus delta x squared here, where these functions are, as usual, modified Bessel functions. This is a k. One. Just one long expression. And what is interesting is when we take the limit in which the separation between the 2 points goes to 0. I said the other day delta x squared is just delta x mu delta x mu, where delta x is just x minus x prime. You cannot see it maybe from Penn State, but just delta x is just the geodesic distance squared between x and x prime. So if you take the limit of this guy when the geodesic distance squared between, so this is the geodesic distance, when it goes to 0, it is given by 1 over minus 2 pi squared, I think. I hope I took the... What is important is that this goes as 1 over the distance squared, so it diverges when delta x goes to 0. We know it because this is a distribution. Minus m squared. So for massless fields, you only have this. For massive, you have additional contributions, which is a logarithmic correction with a constant times the mass, again, the root square of the geodesic distance squared, plus higher order plus m4 over 4 plus so I think I'm not sure. So what is important here, have higher order terms in delta x. So delta x 0 to the power 1 to the power 2 to the power 3. So the important thing here later on in the course is going to be that the leading divergence is 1 over the distance squared, and then you have a logarithmic divergence. And then you have finite terms in delta x. When you take delta x to 0, this one, all this is finite, and you have these two divergences.
Is there this theta of delta x in the second term?
Say it again.
Like, you have a, that's the heavy side function.
No, it's only here.
So
far as I have in my notes. It's already there. The important line is the second one, and this is going to be important later on in the course. I told you that this guy is a distribution because it diverges whenever the distance between them is 0, because you take the 2 points at coincidence, or because the 2 points are related by a null interval. In both cases, delta x is 0. And the divergences are 1 over the distance squared plus a logarithmic divergence, plus finite terms. I just say this here because it will be important later on in the class. Second comment that I think is quite important to keep in mind is that note that the 2-point function, the propagator,
Wait, I've got a question about that equation there. Is that an O or a theta where it says O delta x?
where?
First line.
First line here,
Yeah.
this is the step function.
Okay. But that's an O in the bottom line there, right?
This is order,
Yeah.
right?
Okay.
Sorry. This means order delta x 0 or higher order, and this is the step function. And this indicates order.
Okay, thanks.
So the comment I want to make is that note that the 2-point function, this Hadamard function, and even the Feynman propagator depend on the vacuum state. So they are vacuum expectation values. So if you change the state, if you have a different state, they are different functions. So they have information about the vacuum state. However,
Wait, I'm still confused. When does this equation apply?
which equation?
What you just wrote, what is it for?
This last one?
The whole thing?
The first line is just the analytical form of the Hadamard 2-point function in Minkowski spacetime
In Minkowski's
for a scalar field, right?
Okay.
And the second line is just the limit of this function when the 2 points are very close together. And I just said that this will be important later on in the course, so I just wanted to leave this expression here, so I can refer to it in the future. And the important ingredients is a quadratic divergence and a logarithmic line. Just keep that in mind. However, the propagator, the retarded green function, and the advancing green function do not. You don't need any vacuum state to define these green functions. They are just green functions of the classical equation of motion. So they only know about the equation of motion. Of course, hyperbolicity is crucial in defining green functions, otherwise you cannot. And so the fact that the equation is hyperbolic and the spacetime is globally hyperbolic is crucial. And boundary conditions are important, but you don't need any quantum state to define them.
Can I ask you something? I don't know if you mentioned it before, but what happens if the mass goes to 0?
Then you don't have logarithmic divergence,
There is no logarithm.
but you still have the quadratic divergence. So this is why I wrote this explicitly with the mass there, because this term in the massless limit
Oh, right, there is a mass square.
there is a mass
Okay.
square there.
Mhm. Thank you.
There is a mass there and a mass there, so in that case you don't have logarithmic divergence.
And y1 and k1 are
Say it again?
y1 and
Yes, are these special Bessel functions, whatever they are called, they have many names. And the last comment I want to make, I want to make one more. The one to the last I want to make is that, remember that we have used what people call canonical quantization. So that means that we have taken as the key input in the quantum theory the fact that commutation relations at equal time are given by this. So this was our input. This was what Dirac told us that we have to do. We have to start from the classical theory, phase space, where we have these Poisson brackets, and we have to generalize Poisson brackets to commutators in this particular way, and build the quantum theory. But there are many people who, who this is, I don't know, repugnant or ugly from the relativistic point of view, because you really need to take the space and break it in a space and time, and take correlation functions at a given time. For me, it's not that ugly, because after all, you can do it in the way that you want. But if you really don't like this, because it seems that manifestly breaks Lorentz invariance, then you can do the covariant formulation. So you can do a covariant formulation by taking as your basic commutation relations what I wrote before, that this is given by I h bar, the commutator. Remember that the commutator, this G, is just coming from the wave equation. I don't need any quantum state, no quantum theory to define it. So this equation really provides perfectly valid basic covariant commutation relations to start building our theory. So if you don't like this line, you can start with this line. The commutator of phi, x, and y for any 2 points in space-time are given by the difference between the retarded and advanced grid functions. Remember that G is the difference between GA and GR. And the commutation relations involving pi can be obtained from them taking time derivative. So this is indeed all what we need. So now you can wonder at which extent this line and this line are equivalent. So imposing this or imposing this has the same information, and I just want to give you the result. So let me go over there. So what I want to say is that the equivalence between covariant and canonical formulations is given by the following ingredients. The first ingredient, which you can try to prove yourself, is that this expression where I have phi. This is even true at the classical level, so I don't need operators. So I have partial t g x prime minus g x prime phi not of t x. This is a prime, this is a prime, where x prime is t naught x prime. So what is this equation telling to us? This equation is quite nice because that tells us that, if you give me initial data for the field and its conjugate momentum, so the value of the field and its conjugate momentum at a given instant of time, and I know the propagator, I can know the field at any other point of the space-time. So this is what this propagator is doing for you. It's just taking initial data and giving you the value of the field at any other instant of time. So this is, if you want, the relation between this and initial data. I put quotations in initial because it doesn't need to be initial, it can be final data. And second step, using this relation, if you want, for operators, it is not difficult to show that, I just gave you 5 in terms of initial data. I know what the commutators for initial data are. They are the canonical ones. The statement is that from the canonical commutation relations, and this expression you can get the covariant commutators. So from the canonical commutation relations at some fixed time, and this expression you can get the covariant. So you can prove that they are really equivalent, like they have exactly the same information. And this is nice because this really gives you the relation between the covariant and canonical formulations. So if you want to keep everything covariant, don't talk about any specific time, you can do it if you like it. I don't write it, but the comment that this establishes the equivalence between covariant and canonical formulations.
Okay, by y you meant x prime, right?
By y I mean something else. Thank you. X prime. Thank you. I was using y or not. I have y in mind. Thank you.
There's a Y over there, if that's what you're looking for.
Number 3.
I was using y before. Where my bias coming from. Okay? And the last comment I want to make is just a very quickly comment. I don't want to give you details right now. Is the fact that we have been using phi and pi. I was calling them operators. If you see how I define them via a decomposition in Fourier modes, so as a sum of all Fourier modes. The statement here is that that sum doesn't converge mathematically, even if you use wave packets. So the sum that he was using, these guys, doesn't converge. So from a mathematical viewpoint, these guys are not well-defined operators. So you cannot call them operators in the mathematical way because they are not. And why then we use them all the time? Because we know that they are not operators, so we can keep that in mind. They are very easy to work with, and if you know what you are doing, you are allowed to manipulate them appropriately. But at the mathematical level, they are not operators. However, if you smear them with what we call a test function, or let me call it, with a function of compact support. So you take a function, f function in spacetime, which, I'm going to take it smooth with infinitely many derivatives, and of compact support in Minkowski spacetime. Compact support means that it's defined only on a compact subregion. And smear, what I mean is that you take the field operator and you define this new animal, which is just the integral of the field operator against this function. So you kind of smear the function, the field with a test function. This is a well-defined operator. Is a well-defined. So at the mathematical level, these are the guys that really make mathematical sense. Operator, field operator, smear with a test function. So in this sense, this makes us to call this guy and this guy operator valued distributions. Remember that a distribution is a map functions on something. It's something that takes a function and gives you whatever you want. This is something that takes a function and gives you an operator. It's an operator valued distribution. And you know, you can derive all what you want using operator value distributions, and this is the way that you have to do it if you want to be mathematically rigorous. For example, if you want to work out the covariant computation relations, then you have to give me a well-defined operator. It will be the operator smear with some function. You have to give me another operator and ask what are the computation relations, and you can check that they are given by the function g acting on f and g, where by that what I mean is the integral d34 d4x prime f of x g of x prime. So commutation relations are perfectly well defined for this kind of operators, and you can rebuild the theory using them. I will use them more in later chapters, but I just wanted to leave the comment here so you have in mind that these guys are not operators in the rigorous sense. So more about them in chapter 10 or whatever.
Is that what the brackets on the slides on the presentation this afternoon meant?
I think so. I believe he was using that. And when he was mentioning that, you know, an operator associated to one of these epsilon k, when he was writing this hat, this is what he meant. So this is the summary of Minkowski spacetime quantum field theory. So I went fast in some parts because I assume that this is more or less known material, and if you want to know more, you can ask me or check in books. But at least I presented the information that I want you to have in mind. In particular, you know, the basic construction, which is take the space of solutions, of the space of complex solutions, is a vector space, infinite dimensional, because we have infinite number of degrees of freedom. Decompose it into subspace. One is the complex conjugated of the other. This in such a way that the first one is made of positive frequency modes. Then you have an inner product given by this Klein-Gordon current that I was using to define the inner product. The inner product happens to be definite positive in the space of positive frequency solutions. With that, you can construct the field operator as a linear combination of the basis of positive and negative solutions. The coefficients are A and A dagger. You can show that they satisfy the algebra of creation and annihilation operators. So you can define the vacuum as the state annihilated by all annihilation operators. From it, you can construct the one-particle Hilbert space, and from it, the Fock space. And then you have a representation of the field operator on the Hilbert space. Commutation relations, canonical or covariant are satisfied, and you have a full quantum theory, and you are ready to do computations. So,
just one with like, why do we restrict ourselves to like one particle Hilbert space? And like in today's talk also, like he was talking about one particle Hilbert space.
because it's the basic, because the Fock space is just built on the top of the one particle Hilbert space. So, you know, if you want, the one particle Hilbert space is a subspace of the Fock space, but it is what you need to define the Fock space. So, you know, if you give me a one particle Hilbert space, I know what the Fock space is. Yeah. You know, the Fock space, it is built, if it's symmetric or whatever, or antisymmetric if you are describing fermions, is made of direct sum of direct products of one particle Hilbert space. So it's just, you know, it's one particle Hilbert space to the 0 power plus one particle Hilbert space to power 1, one particle to power 2, etc., etc. So if you know the one particle Hilbert space, you have characterized the Fock space. So this is why he was mentioning only that, because So any question? If not, we can start discussing the time-dependent situations.
I have one super quick question.
Please.
The field operator and conjugate element, you said that they did not converge. In what sense? Because they're a Fourier transform of, I just want to say, A plus A dagger.
No, in particular because they are Fourier transform of stuff that oscillates with arbitrary large frequency.
Oh, arbitrary frequency.
Right. So
Okay.
you have the sum for all k of omega. Omega depends on k, but it grows with k. So you have.
So when we
oscillation.
smear it with something, it's almost kind of like a weighting function.
Exactly. Because it's of compact support, so this guy has a Fourier expansion which decays faster than an exponential for larger k, for large
Okay.
k. So this kills that bad behavior.
Okay.
So this is why you need functions of compact support. So rigorous people, they talk all the time about operator value distributions and about these kinds of operators. In textbooks of quantum field theory in cosy space-time, you don't see that often. People work with phi of x and phi of x. They know what the problems are, but you can still manipulate them and get information about the theory and even get predictions without entering in those mathematical details. So if you are more mathematically oriented, you can think on this. If not, you can't. This is the good part of living in a free world, more or less. Okay, so what I want to do now is to move to the time-dependent situation. So, as I did for the time-independent, there are different levels of construction. I started with the harmonic oscillator because I wanted to show you in a simple case how to build this space of solutions, a space of complex solutions, how that gets separated in positive and negative subspace, how you build an inner product. In that case, because it's very simple, and then I repeated it for the quantum field theory, where it's just doing that infinitely many times, one for each k. Now we want to do the same. First of all, I want to show you what happens with the harmonic oscillator when you lose time invariance. So when you have a constant k for the spring, which depends on time, and what is going wrong with our previous construction and how we have to generalize it. So that will give us, in a simple situation, a clear view of the new features that appear when you have time-independent situations, time-dependent situations. And then I will go in the next chapter to quantum field theory in complex spacetime. But if I do it for the harmonic oscillator, and with this chapter, quantum field theory in complex spacetime will be almost formulated by ourselves. So again, it's very important that you understand the situation for the harmonic oscillator, because if you understand that, then you are going to understand the quantum field theory. If not, you are not going to. So chapter 3, the time-dependent harmonic oscillator. Dependent harmonic oscillator. And here I want to discuss the quantum theory. Then Bogolyubov,
Is Bogolyubov?
Bogolyubov transformations, and 3 spontaneous and stimulated creation of quanta. So let me start by the quantum theory. So first we have the classical Lagrangian. L kinetic energy minus potential energy. But now K depends on X, on T. So and I want to take K a smooth function of T. So take it C infinity if you want. So we don't have problems. And so the first thing is that time translational symmetry is lost. So our Lagrangian is not any more invariant under time translation, so energy is not going to be conserved, and we don't have that big symmetry on our theory. So taking variations, the equations of motion are the same as in the time independent case. The only thing is that now the frequency depends on time, where the frequency again is defined as the root square of K function of time over n. So now we can try to follow the approach, the quantization approach that we used in the previous situation. And so, but if we do that, we find quite soon a difficulty. So remember, what we did today was, first of all, positive and negative frequency solutions, and write X as a combination of positive and negative frequency solutions. First difficulty, they are not solutions of this equation. So positive and negative frequency modes, frequency functions, or frequency modes, e to the plus or minus I omega t over root square of omega m are not solutions of equinox. Of equation 1. So you can put this over there and you don't find. Where of course this omega is some omega naught, some constant. Or you can use omega of t and you will find that there is no solution. So there are simply no solutions which oscillate with a given frequency. And of course, this is a consequence of losing the time translational symmetry. So there are no solutions which are eigenfunctions of partial t. This is what a solution with definite frequency is. A solution which is an eigenfunction of this. This is an eigenfunction of this. But you know, if you want, the differential operator here doesn't commute with the partial d operator, so there are no solutions with definite frequency.
So when you wrote the positive negative frequency modes with that omega e to the I of t, that omega is a constant omega?
You can choose that the same omega, or you can choose wherever.
Okay, if it's a function of time, it's still not solutions?
No, it's not a solution.
Okay.
Because you know, this will hit derivatives of omega, and that will not be satisfied. So these two dots will hit this omega, but even if you put a constant omega, it will either, because this omega depends on time, so you will never get a zero. So simply, there are no solutions with definite frequency. So, and that is, of course, a consequence of the time translational symmetry. So therefore, we don't have a natural decomposition of the space of solution. So we don't have a natural decomposition S in two subspace, one the complex conjugate of the other, with this positive frequency and negative frequency. That structure is not available in our theory anymore. So the strategy followed in chapter 1 doesn't generalize. So do you have any suggestion? What can we do in this situation?
We choose an arbitrary sort of decomposition of possible solutions.
Almost.
Is there some natural choice?
Almost. So what I want to say is that, however, but the more compact formulation has the clue. So the most, I just summarized 10 minutes ago what the most compact formulation is. Remember that we have this decomposition, and we have an inner product, a product which is positive definite in the space of solutions, and with that, this was our mathematical elements, and with that we derive everything. So the key point here is the following. The key point here is that in chapter 1, we made this subdivision using the notions of positive and negative frequency. And then we realized that this product is positive definite in this guy and negative definite in this guy. Now we don't have the frequency to decompose it, but we still have the inner product. So the key element here is going to throw away the criteria of using positive and negative frequency to split the space of solution and use the inner product. So the strategy is do any splitting that you want such that the inner product is positive definite here and negative frequency.
Is the product going to be the same definition as we use last
Exactly the same. The product is always the same. So repeating, we use positive and negative frequency decomposition, and we realize that this guy is positive here and negative here. That last property is what we are going to use to generalize the theory when we don't have positive and negative frequency.
Are there unique choices of spaces such that is positive definite one?
I will go over that.
Does this have to do with killing vectors?
One by one. One at a time. So, I mean, killing vectors are similes of a space-time metric. We are with the harmonic oscillator. We still don't have any. But you know, killing vectors give you symmetries, and of course the symmetry is what gave us before in chapter 1 the positive and negative frequency decomposition, because symmetry under time evolution means that we have solutions with positive and negative frequency. Now we don't have that symmetry, so we don't have that available anymore. But we have our inner product, and this is what we are going to generalize. So the strategy is going to be formulated as follows. Remember, we have the space of complex solutions. We have SC. The only thing is that we don't know how to split it in two parts because we don't have the previous criteria. So choose any solution. Remember here that the space of complex solutions is two-dimensional.
The SC in the previous case, that still is the solution for this equation?
No, of course, the equation is different. So we have now the analog space of solutions. So you have to take that equation and build the space of all complex solutions. It is too complex dimensional, because the equation is a second order differential equation and we are talking about complex solutions. So too complex dimensional. It's different from the other one, of course. This is why this exponential of minus and plus omega d doesn't belong to our new space of solutions, because our equation is different. So we don't have those modes on our space anymore. They are not solutions. So So the way I'm going to define S plus is as follows. S plus is one complex dimensional. Choose any solution, phi of t, a classical solution. With positive norm. So the norm is that you don't see. Again, we still have the same inner product. The inner product is the same. You know, remember that the inner product is I m.
Is it an inner product?
It's a product. It's an inner product only inside S plus. So it's, at this point, you're
But we
right.
don't know S plus yet.
Exactly. So at this point, it's just a product. So it was bar phi conjugated, bar 2 plus dot plus dot 1, bar 2. So the product is exactly the same. And you can see that this product is conserved on that. But the space of solutions is different. So this was just to refresh your memory. So choose any solution which has positive norm. Choose it normalized for convenience. So normalize it to have norm equal 1 for convenience. Then this gentleman spans a one-dimensional complex subspace of S, which I'm going to call S plus. In which the product is positive definite.
And now we just need to find something orthogonal.
Right, which is the complex conjugated.
Okay.
So S minus is the complex conjugated of S plus. As a consequence, the product is negative definite in S minus. And also as a consequence, S minus is orthogonal to S plus automatically. And also the total S is the sum of S plus and S minus.
Would you want with something with inner product 0 line?
Any real solution has zero norm.
Yes, like I mean, where is it? Like, I mean, both are taken to be strict, like positive, different, positive.
So in the space there are vectors which have zero norm. It's like in Minkowski spacetime. There are vectors with zero norm. But if I ask you to find a vector in Minkowski spacetime with positive norm, it's going to be a spatial vector. So by choosing this, I am sure that you are choosing a complex solution. Because real solutions, you can check real solutions. If you write the product and put something real, it's going to be zero trivially. So this condition selects complex bounds.
I have a question.
Please.
Is that condition preserved upon evolution?
Yes.
Okay.
The inner product is preserved. The inner product,
So if-
remember,
If it is positive,
it will be positive.
it will be positive forever.
If it is 1, it will be 1 forever.
Right.
This is why I spent some time defining the product, because I wanted a product which is invariant under time evolution. And this is true still in our equation. I didn't say that explicitly, but the inner product for that equation is also constant in time. Otherwise, it's not even a product, because it depends on time. So by product, I mean some bilinear map which so two functions to a number which is invariant under time evolution. So if you choose some solution which has positive norm, let's say norm equal 1, then you are done. At a given time, then you are done. You'll have the same norm forever. That expands S plus. The complex conjugated expands S minus. And S is the sum.
Is the norm a function of time?
The what?
Is the norm a function of time?
No, this is what I just said. That the norm is time independent.
Norm is time dependent. Okay.
Otherwise, it's not even a norm.
But the product is time independent as well?
Right. I mean, the norm is just the product.
Not,
by
not even just the norm, but the product between any two things is time
time
independent.
independent. Again, that is a key property of the product. If the product is not time independent, I will not even call it a product.
We checked that and that still holds.
Right. Even though I have changed the equation, now the equation is different, but still, you can check that the product is time independent with that equation.
Okay.
I should emphasize that more, so I apologize. We still have the same product, and the same product is still time independent. But look at, we have what we wanted. We have an inner product and a split of the space in two subspaces. One is the orthogonal of the other, and in one of them the product is positive definite. So we can build the quantum theory.
Okay, we just need to find a solution first.
Exactly. So we have replaced the condition of this guy be a positive frequency mode. Now we don't have that choice. I have replaced that by the condition that this guy has positive norm. Positive norm is general for any space for any function here. You know. This condition is going to I can apply this condition for any arbitrary omega of t. The previous condition of positive frequency is restricted. I can only use it in time independent situation. So now, you just build x of t is going to be some operator, your basis plus dagger, your basis. I have a quantum operator. The momentum is going to be m times x dot. I don't have even to write it.
And so far this basis is arbitrary.
Arbitrary.
depending on what
Arbitrary.
we pick first. Yes.
Exactly. Arbitrary. This is the only condition I have imposed so far. I will talk about the freedom in a second. So now you can write this expression for the operators where a dagger is going to be the product of your mode, your basis mode, and the x operator, and a dagger is going to be minus the mode conjugated x operator, and you already checked in chapter 1 that if the modes are normalized, I mean, even if they are not normalized, A and A dagger are going to satisfy these commutation relations, which if the modes are normalized is equal to 1. A dagger with a dagger give us h bar phi star, which is 0 by definition, and a dagger h bar phi star product with phi equals 0. So we are guaranteed by our mathematical construction that these two operators are creation or annihilation and creation operators. And 5, the vacuum, is defined as the state such that it is annihilated by the annihilation operator. And now the one particle Hilbert space and Fock space are defined in the standard way. One particle Hilbert space and Fock space. Space constructed in the standard way. So we have our theory.
everything we did here, we could have easily just done before as well, so we haven't even attacked what the time dependency of LCM, right?
Very good point. So the answer is completely yes, and I will mention LCM. So we have full theory. We have a Hilbert space, which is our focus space. We have representation of X and P operators. They are self-adjoint. They both satisfy the equations of motion. We have a theory. We are ready to do computations. Go ahead. You look puzzled.
Last time we found it useful to decompose it into an infinite number of,
But that was in field theory.
right, why did we find it so useful to do that?
Because we were in field theory, and in field theory you have infinitely many degrees of freedom. Now I step back to a single harmonic oscillator, so we only have one single degree of freedom.
We'll get there.
Okay,
So I will go to field theory after this example.
okay,
Like this. So,
okay,
So-
so we're not done.
no, we are not done. This is just for a single harmonic oscillator. I will next chapter will be quantum field theory.
We'll
and-
soon get infinite many.
Right, and we'll get infinite many of this. I'm just doing this here because we only have one. It's more clear mathematically, so I think it's more pedagogical to do it in this way than it is now.
No, I wasn't objecting to pedagogy.
Okay,
I
so
was just confused by the word unstatement.
okay, we're not done. Of course. We are in the fifth class. Third week of class. Okay, so everything is pending of my choice of a single solution, complex solution, which has negative norm at a given time. From that choice, I build the quantum theory. So the first thing I want to do is to give you an example. In a practical situation, how can I choose one? Give me an example that you choose one. Example. Let me imagine that I have a time-dependent frequency omega, which is just exponential of time. I just write this to have nice analytical solutions, otherwise. So, to find an instance of solution with positive norm, I'll take advantage of two facts. But well, the first fact is that a solution, any solution, is uniquely determined, is in one-to-one correspondence with initial data. So if I give the velocity and the value of the function at a given time, I uniquely characterize the solution. Second, as we have discussed, the norm of the solution is time independent. So if I choose the norm to be 1 at a given time, will be 1 forever. Therefore, all what I have to do is to find initial data with norm equal 1. If I find that, I will have a solution satisfying what I want. So, therefore, all I need to do is to find initial data with norm equal 1. Equal 1. This is extremely nice because initial data doesn't know anything about the equation of motion. So I can choose the same initial data that I was using in a time independent situation. The initial data doesn't know about the equation of motion. So I'm going to close my eyes. I'm going to choose initial data as if I was working in the time independent situation. That initial data has norm equal 1, and therefore there is a unique solution to my equation of motion with that initial data. That solution is what I'm looking for, or an example of what I'm looking for. So, a possibility, because this is just an example, there are infinitely many. A possibility is to choose initial data as if our solution had positive frequency at T naught. So let me use T naught equals 0 just to have simple equations. So I'm going to choose phi of 0 as e to the I minus I omega naught time equals 0 to omega naught, and the derivative, this is my choice, minus I omega naught into the minus I omega naught 0 to omega naught. Of course, the phases are equal to 1 because I am choosing time equals 0. I just write them so you see what I mean. And I can do this because the initial data doesn't depend on the equation of motion. So you can check that this initial data has norm equal 1, and therefore there is a unique solution. So the solution phi of t with this initial data is the following: phi over 2 root square of 2 omega naught mass, and now I have these Bessel functions y that depends on e to the t omega naught minus I j naught of 1 plus j1 of 1 plus j naught e to the t omega naught I y0 of 1 plus y1 of 1, where j mu and y mu j mu of x and y mu of x are Bessel functions of first and second order. So this guy has norm equal 1 at any time, of course. I found what I was looking for.
Are there supposed to be factors of m in the phi 0 and phi dot 0?
Yes, thank you. No, I have that, of course. I forget, because in quantum field theory we don't have that. So this is an example of finding. Take one time and give initial data as if the mode was positive frequency. Of course, the solution is not positive frequency at all. This is not exponential of I omega t at all. This is much more complicated. Of course, if you use a different time to put the same initial data, you will get a different solution and you will get a different decomposition. So this is just one example. One very simple way of choosing initial data at one instant of time.
Is that y naught of e to the t omega naught?
Yes. So let me just, I want to make, go ahead.
Can you read off the subscripts of the y and j in the solution that you wrote?
Sorry.
It's Let's see. Phi t equals to
So 0,
yeah.
0, 1, 0.
Okay.
Thank you, I just keep forgetting.
Okay, good. Okay, good.
And this is just a mu.
And they are functions of time.
They are functions
right?
of time. This is e t omega naught, e t omega naught. Except those ones that they are evaluated at 1. Those ones are numbers.
Okay.
So it's just a combination of y,
Okay.
y naught and j naught with some numbers.
Good. Thank you.
If you don't
Good.
like
Thank
it,
you.
ask Mathematica.
Okay, sure.
So now what I want to do is to make a few comments, but I'm going to stop here. So just the first comment I will make next day is that we have separated our space of solutions in two parts. Now we shouldn't call them positive and negative frequency subspace because they are not. We should call them positive and negative frequency norms. Still, people use positive frequency subspace and negative frequency subspace all the time. Today, in today's talk, Abai was talking about positive and negative frequency subspace. Maybe there, in that region in the Sky class, you have that. But in general, people talk about, still call this guy positive frequency subspace, even though the functions are not positive frequency norms. But just, it is more correct to call them positive norm subspace. Second comment I will make is how much freedom we have here. We have choose. There is a choice here. Choose one function which has positive norm. So how many different ways I can do this? Answer, infinitely many. And we will see. So we will have infinitely many quantizations and we will see the relation between them. And I will build on that. But very important, please understand this construction. To me, if you understand this mathematical construction, you have all what you need to understand quantum field theory in coarse spacetime. If you don't, you will not. So this is a key element in our theory. Understanding that in time-dependent situations, you don't have the notion of positive and negative frequency modes to do your quantization. But you still have your inner product, which is your guidance. You can use it as a guidance. Separate S in two subspaces the way you want. But besides that, this is positive norm, and this is negative norm. And then build your theory. So, questions now?
I kind of, in what we did earlier, we had a Klein Gordon field. You went through the fluid theory. We had the intuition that every point in space kind of has this harmonic oscillator. And we established what we did. Now, with the time-dependent theory, are we running through the same thing where we're saying every point in space not only is a harmonic oscillator, but also time-dependent?
Right, something like that. But I wouldn't say every point in space. I would say every Fourier mode. You take the field, phi of x and t, you expand in Fourier mode, so sum on case, or integral on case.
Okay.
And each k behaves as a complex harmonic oscillator. Now, in time-dependent situations, we will have exactly the same.
Okay.
Infinitely many time-dependent.
I'm just curious what's motivating our interest in time-dependent
Right.
stuff.
Right, because in an arbitrary metric, a scalar field is a sum of infinitely many time-dependent harmonic oscillators.
Okay.
So we will repeat this infinitely many times. It will be completely parallel to what we did.
So in curved spacetimes, our metric is actually sort of a function of time-dependent harmonic
Right.
oscillators?
Right. So a metric in GR is a function of x and t. The Minkowski metric is constant everywhere, and they have symmetries, time translations,
Okay.
spatial translations, boost. In an arbitrary metric,
In curved spacetimes, if I move around,
right,
yeah.
like a black
My
hole,
metric
if you are close to the black hole, you are going to die. If you are far from the black hole, you will survive.
So only difference was like finding solution for time dependent and time independent case. Like
How difficult or how?
no, like the only difference, I mean like conceptual difference, I mean whatever our formalism is finding solution for time dependent and independent.
Right. No.
Rest of it
I mean, the main difference is really time. In this case of the harmonic oscillator, is time translation invariant. The theory is time translation invariant. That implies that there is a preferred set of solutions, which is exponentials of I omega t. And you will see that in that one, I show to you that if you use, you can ask me why e to the plus or minus I omega t is a preferred set of functions. First of all, because they are eigenstates of the generator of our symmetries, which is partial t. This is the time translation vector field, and these functions are eigenstates of that operator. So they are telling us that they are really associated with that. If you want something more physical, I show to you that the vacuum state that we build using those modes is invariant under time translation.
But now that's not true in this time-dependent case.
Exactly. But even in the time-independent case, if you want to use a different basis, not by this, you can do it. You will get a quantum theory, but the quantum state, the quantum vacuum, will not be invariant under time translations. And then, symmetries tell you what should be the right vacuum.
But nothing's stopping us from doing any
No,
of that,
nothing
or
stops
making
that.
different
No.
physical predictions
This
in
is-
any sense.
I will describe that in detail. That in that case you have a preferred choice. Symmetries tells you what is the most reasonable choice. You want a vacuum state which is invariant under the symmetries of your theory. Would be and also to be the grounded state of the Hamiltonian. If you do something else, you will get a state which has non-zero energy, and there is no reason to call it grounded state. But I will go over that in more detail next day. But please read this again and be sure you understand all these mathematical
So-
statements, because they are really
The
difficult.
important part that you're trying to drill into our head right now is that using this method of having this product, finding a space of solutions through some arbitrary any choice of solution which has positive and maybe normalized norm, allows us to build up the quantum theory.
In an arbitrary time-dependent situations.
Okay.
Yeah, so in like both cases, like what we have taken is like simple harmonic oscillator model, right? Like without any damped oscillation, like
Right,
without any
right.
constant
But this will generalize if you have a damping oscillator or whatever.
Okay, this one.
Right, this generalizes. As far as the question is linear, if it is non linear, then you have to do something else. But for a linear theory,
Yeah, for linear one. Yeah.
Because
Then omega, that quantity.
if it's non linear, then you have to do this for the homogeneous solutions and then do perturbation theory to build.
Yeah, so like in your model, I mean, like in your actual research, what like this suffices, or like people
This is
consider-
sufficient to discuss Hawking radiation, to discuss inflation. This linear theory is sufficient. In inflation, if you want to compute non-Gaussianity, that is non-linear. But in general, with the linear theory, to compute the C and B power spectrum, to compute Hawking radiation, to compute the Unruh effect, this is just purely linear. Everything is going to come out from this time dependence of the space-time. Here, the time dependence of the wave equation.
I have a question. In the time-independent case, we just made the argument that there was one really sweet choice of basis, which made things very nice for us and have
Right.
a ground state and vary
Exactly.
through time and such. Now, we pretty much picking solutions out of the dark to build our basis.
Right.
Are different or perhaps better choices of bases, can I say, would
No,
some be a
not.
bit more easier for us to work with in that kind
In a
of
generic situation, in a generic omega of t, so for a generic, no, there is no preferred.
Okay, so
And I presented this in this way, in the time-independent case, we didn't even realize we were making a choice, because
Yeah.
the basis was so sweet that, it is but when you come here, you realize that basis is not anymore. That sweet choice is not anymore. So you're, come on, now what do? I don't have what I believe it was the natural way, or the only way. Then you look back and you realize that, no, that was not the only way. That was a sweet choice, but there are many more. Now I don't have the sweet one, but I still have the other one. So I'm going to do systematically all the other ones.
okay.
So next day we will keep going. So please read that by yourself, sit down, and be sure you understand it. More questions?
I have a pragmatic question.
Pragmatic.
Over the weekend, no homework except rereading?
I feel like that's
Don't.
important.
I think that is a very good homework.
Yeah.
Excellent.
For a given form of omega t, are you saying that even if I specify omega t, I still have different choices for phi t, which have positive no?
Exactly. Look at.
So, but
I give you.
essentially,
I gave you an example, but it was choosing t. No, if I do the same, choosing t not equal 1, I will get a different solution.
Yeah, but if I choose one of the phi t, and that phi t is the basis for S plus, right, which is the space of positive norm solutions, then any other solution is supposed to be
No.
like
No.
because it's the basis of that space.
I will go over that next day, but if you want the solution quickly, so imagine, I'm going to say what I will repeat next day, but take Minkowski spacetime, one inertial observer. The metric is indefinite, so there are vectors with negative norm and vectors with positive norm. Now, this is Minkowski in 2 dimensions, just to simplify. I asked you, can you decompose this space in a subspace with negative norm and a subspace with positive norm? You can say yes. This, for instance. So let me call this, I don't know, S plus, and this is minus. Or the other way around, because my convention, this guy has negative norm. Negative, positive plus negative. But now, somebody else comes and says, no, I have a different one. I can choose this as, this is still time-like. This is a different S minus twiddle, and this S plus twiddle. And this, the sum of them is the same, but they are not the same one-to-one. So this is not the same as this, even though the sum of both give you the whole Minkowski space. So you have infinitely many ways of decomposing Minkowski space in 2 subspaces. And they are inequivalent, because this is not the same as this one.
But are they like isomorphic? I mean, like, can the number of elements in each can be mapped to other, or like is it
Of
Well,
course,
the total space of solution's the same, no matter what.
Any vector space based on the same the complex numbers with the same dimensions are isomorphic to each other. You can take basis and identify the basis, but they are really different. And I will go over the physical consequences of this. So I will go over all your questions in full detail. So I am just advanced something that creates more questions. So just understand what we have seen right now, and next day we will build over that and we will extract physical consequences. Questions at Penn State?
No, we're good. No, we're good. Thank you.
Sure.
Thank you.
Penn State knows their field theory. Penn State seems to know their field theory.
Even the janitor.